Let us now discuss the last phase of instruction processing, which is the instruction commit phase. So we typically use this phase to release resources, remove instructions from the pipeline, and also ensure precise exceptions. So what have we been discussing up till now? What we have been discussing up till now is out of order inside, in order outside. So instructions enter in order. Mind you, they are perceived to be executing or leaving the processor in program order. So it is important to note that perceived, in a sense, that's what an observer perceives, even though the execution is actually happening out of order. So for an external observer at any point of time, the instruction flow can be paused. This is a corollary of in-order execution, that if instruction execution is in program order, well, we can pause it at some point and resume it at exactly the same point later on. Alright, so that is the most important aspect of out of order execution. So what we will do, the core structure that we will add over here is the reorder buffer. It's called the ROB, right? The short form of a reorder buffer is ROB. It contains one entry for every instruction that has been fetched. Alright, so similar to other structures, it's a queue. Similar to the instruction window, for example, it's a queue. So after decoding an instruction, we enter it in the ROB. So as soon as we have read the instruction and we have decoded it, it's entered into the ROB. And needless to say, all queues that we have in an architectural setup, they are implemented as circular queues, right? Otherwise, there is no other way to implement it with using a finite sized array. So they are implemented using circular queues. So when we decode an instruction, we enter it into the ROB. That's the important point over here. If there are no free entries, right, so if the ROB is full, which means that instructions are not able to leave the pipeline for some reason, we'll see what are the reasons later, then the ROB will essentially become the bottleneck. The decode process will stall. This means that the fetch process will stall and the entire pipeline will stall. So pretty much the ROB maintains a record of all the instructions that are in flight, which means within the pipeline. So let us call this in flight instructions. Right? And it's pretty much an in-order queue where when we decode, we enter, and they leave when what we call instruction commit or instruction retirement. So when do we update an entry? Well, so the instruction remains there. After we decode, the instruction remains in the ROB. As soon as an instruction finishes its execution, which means it computes its value and it is done, we update the entry of the ROB, we mark it to be ready. So there is a ready bit in the ROB, we just mark it as ready. So what do we mean by finishing its execution? Well, an ALU instruction finishes its execution when it has computed the value of the output register. A branch finishes its execution when it has computed the outcome and the target. A load instruction finishes its execution when it has read the value from the memory. So let's call it read the value. Alright. So that's what we mean by finishing. So I'm deliberately mute about the store because we will see that the store is a special case, and as we have argued earlier, a store is only sent to the memory system when it is the earliest instruction in the pipeline, which would basically mean that it's at the top of the ROB, so there is no instruction earlier than it. That's when we actually send it to the memory system. So hang in there, we will discuss the case of stores over and over again in the next few slides. Removing an entry, well, removing an entry is easy, we just remove it from the top. It's called retiring or committing, and of course instructions are removed in program order. It is a loaded statement, keep reading, keep watching. So what do we exactly mean? So what we exactly mean is that our fetch and execute stages. So the moment we decode, right, we create an entry, we add it to the ROB. After finishing execution, we update the entry. So essentially we set a ready bit. We make it known that the operation associated with the entry has completed. So the ROB is updated. Now the ROB is not updated, the entry in the ROB is updated. Furthermore, every cycle we inspect the earliest entries of the ROB. So maybe we inspect the earliest. If that is ready, if it's done its job, we just remove it. Then we inspect the next. If that is done, we remove it. Then the next. So how many do we inspect at most? We inspect W entries at most, where W is called the commit width. It's typically 2, 4 or 6, so let's assume it's 4. So what we do is that we inspect the earliest. If that is ready, well, we just remove. If it's not ready, we don't do anything. We stop there. Then we inspect the next one, the second earliest. If that's ready, well, we remove it. If not, we stop there. So on and so forth until we reach the limit, which is the commit width. So the commit width essentially determines the rate of instructions exiting the pipeline. So we typically set the fetch width equal to the commit width, because if you look at the pipeline as sort of an instruction processor, on an average, if we are committing 4 instructions per cycle, we should also be fetching that much, otherwise it will lead to a rate mismatch. So now coming to the commit, well, the commit process is entirely in order, which basically means that we keep inspecting the entries earliest first, right? And we stop at the first entry which is not ready. So if it's not ready, we just stop there. So it's never the case that we commit an entry but an entry earlier than it is still there in the ROB. So that never happens. And until we reach the W8 entry, so we have a limit on how many instructions we commit per cycle. Alright. So we pretty much commit all the earliest entries that we find to be ready in program order, right? So we never skip any entry. What is the advantage of doing this? Well, let's see. What does it mean to commit an entry? Well, one is removing it from the ROB. So this pretty much removes it. Removing it from the ROB is tantamount to removing it from the pipeline. So that is what this amounts to. Furthermore, removing an entry also might involve additional processing, right? Might entail additional processing. So it depends on the type of the instruction. For example, if we have an instruction with a register destination, like an add instruction, let's see. So here we will answer one of the key important questions of when we release a physical register, put it back into the free list. We'll answer it now. So consider instruction J, let it be R1 is equal to R2 plus R3. Assume that R1 is mapped to PY. So assume that at this point R1 is mapped to PY. Before this instruction, right, so before instruction J came and it was renamed, let us assume that the mapping just before R1 to PY, the mapping was R1 was mapped to PX. So what happens? Well, R1 was mapped to PX, then instruction J came and it changed PX to PY because it got PY from the free list. Now the question is, when can we flip PX, right? So it's a question of register release. So after J commits, after J is removed from the ROB, from the pipeline, right? there are no instructions earlier than J in the pipeline. So this should be rather clear that the reorder buffer ensures that once J is removed, there are no other instructions that are earlier than J, right, that precede J, which are still in the pipeline. Important insight. Let's keep this in mind. So this is very important. Let's keep it in mind. This means that there is no instruction that requires the value in Px. So this is correct because R1 was mapped to Px. Then a couple of instructions maybe came, a few of them might be using Px. Then R1 got mapped to Py, and this was a direct consequence of renaming instruction J. So once J is committed, it implies that all the instructions before it that precede it, they are also committed, which means that all the instructions that possibly use Px, all of them are committed and all of them have left the pipeline. Let me repeat the last statement, rather important. All of them have committed and all of them have left the pipeline. This means that Px can be reclaimed. Alright, so this means that at this point Px can be released and added to the free list. This is undoubtedly a very important insight for us. So this essentially says that whenever I am renaming an instruction that has a register based destination operand, I need to remember the previous mapping. So at this point the previous mapping is Px. So when instruction J is committing, we can't release Py, that is important because consumers of Py will still be there in the pipeline. But we can definitely release Px because Px's use is over, right? All the instructions that were using Px, all of them have been committed, we know that for sure, direct corollary of in-order commit. So what is essentially left is Py and its uses, so Px can be released. So what is the update we need to do to the renaming phase? Well, the moment we see an instruction of this type, where R1, let's say in this case is R1, so it can be any Rx that is being written to, we remember the previous mapping of R1 by reading the rename table. So this does complicate the rename table, by the way, adds additional ports. So we assume that R1 was mapped to Px. So we save this mapping in the ROB entry for instruction J. When J is committed, we unmap Px, which means we return it to the free list, such that the registered Px can now be given to other instructions, right? Can now be assigned to other instructions. This can be done for all instructions that have a destination operand that is a register, right? So these will be ALU instructions, load instruction and so on, where the destination operand is a register. Alright, so this should at this point be easily understood that when we actually release registers, well, we release when the instruction that overwrites the register, when that commits. Now let's come to loads and stores. So when should a store be written to memory? Well, we have discussed this in the past. Just a quick reminder. When we are sure that it's not on the wrong path of a branch and no interrupt will come before it. So as long as there is an instruction before it, earlier to it, that precedes it, that instruction might suffer from a fault and we don't want to take the risk. So only when we are committing a store, which means when it becomes the earliest and it's being removed from the ROB, that is when we send the stores to the memory, right? At commit time we send the stores to the memory, and that is when they actually take effect. So this is clearly happening in program order, right? So there is no doubt about it, and that's when it takes effect. At the same time we remove the entry from the store queue as well. It's not required. With the store queue, all that it was doing is that it was essentially providing temporary storage, right? Which in itself is an important service, no doubt. And loads were supposed to check this temporary storage first before actually going to the cache, right? So this solves the question about stores. that when we are about to commit stores, we actually send them to the memory system. Now, when should a load be removed from the LSQ? Well, this answer is also obvious. We have touched upon this. So the answer for this is that again at commit time, we remove the load from the LSQ and from the ROB as well. So we just remove it from the pipeline. Next question. What do we do in the case of an interrupt? So let us treat interrupts, exceptions, and mind you, this is very important, and this is a question that many people would ask when we talked about branch predictors about recovery. But this question is being answered now, that interrupts, exceptions and branch mispredictions, let them be placed in the same category as exceptional events. So whenever we mispredict a branch, let this be treated as an exceptional event. So whenever we receive any of these notifications, we'll clearly have some instructions in the pipeline that are on the wrong path. And if they are on the wrong path, well, they should not be committed, right? So they should be removed. So let us look at interrupts and exceptions are easy to handle. We just mark one of the instructions the same way we did in an in-order pipeline. And we just wait for that instruction to reach the head of the ROB. So this means that all the instructions after the interrupt, after the marked instruction, they have completed and nothing is completed before that, right? Because we don't make permanent architectural state changes before commit time, right? Now using the ROB, well, let's look at using the ROB primarily for branch mispredictions. The others are simpler to handle. So whenever an instruction has an exception or suffers from a misprediction, we mark it. So for example, if a certain branch is mispredicted, all that we do is we just mark it. We don't do anything else. So we can either mispredict the outcome or the branch, but all that we do is we just mark it. So we just mark the instruction, which means that we remember that this instruction was mispredicted and we don't do anything else. We wait for the instruction to reach the head of the ROB, which means we wait for it to become the earliest instruction. In the case of an interrupt, well, we can mark any instruction that we choose, but if we want the interrupt to be processed as soon as possible, we mark the topmost entry in the ROB, which is also the earliest entry. So that is what we mark. We wait till the marked instruction retires. So retire and commit is something we'll use interchangeably. So we wait till the marked instruction reaches the head of the ROB and is ready to commit. Then we initiate what is called a recovery sequence, which is described in the next slide. Let us now look at a visualization of the pipeline. So in the pipeline, we'll not show much. What is shown here is the fetch unit. The fetch unit fetches instructions. They pass through the rest of the pipeline, and finally the reorder buffer maintains a record of all the instructions that are in flight. So this animation will nicely show you all the processes that are involved. So initially what we do is we fetch an instruction, and at decode time it is added to the reorder buffer. So if we fetch 5 instructions, as we are doing right here, they are getting added to the reorder buffer. Alright, and so we have now fetched and decoded 5 instructions, and you can see that all these 5 instructions are present in the reorder buffer over here. Now let's assume that the instruction that was fetched, the latest instruction that was fetched, that suffers from a branch misprediction. In this case, the 4 earlier instructions, which are these instructions are safe they are on the correct path. Hence they should be committed. Whereas this instruction as well as instructions before it, which means the instruction that mispredicted and the instructions that were fetched after the mispredicted instruction, these instructions should not be committed and they in fact should be removed from the pipeline. So what do we do? Well, we just commit the earlier instructions, keep committing, keep committing, keep committing, and wait for the mispredicted instruction to reach the head of the ROB, the top of the ROB. Once it reaches the top of the ROB, well, something needs to be done. Also, please bear in mind that even though we are not showing, other instructions might have been decoded and might have entered the ROB after the mispredicted instruction, so they will be at these positions. Alright. So it doesn't matter. So when the mispredicted instruction, or let's say an instruction that suffers from an exception, or an instruction which we mark because of an interrupt, the moment it reaches the head of the ROB, which means that it becomes the earliest instruction in the ROB, what we do is that we flush the entire buffer. So we flush not only the ROB but the entire pipeline. This includes the load store queue, the instruction window as well, along with all the internal pipeline registers and buffers. We flush everything. Alright. So what is the recovery sequence? The recovery sequence is that we flush the pipeline. What exactly would this mean? This would mean flushing the reorder buffer. This would mean flushing the load store queue, the instruction window, and all other internal structures. They're all cleaned up. We remove entries from the instruction window, LSQ ROB. All internal pipeline registers, etc. also we remove the entries. And then the most important part is that we restore the state. So before this, I would like to make an important point. So what exactly was our architectural state? It was the program counter, the set of architectural registers. So they here only exist in principle. Then we had the memory state. So since we send stores to the memory system only when they commit, the memory state is correct. The set of architectural registers, we need to ensure that it is correct. Well, it has to be correct. We will see why. The reason is that whatever was the current mapping when the branch was fetched, those physical registers have still not been touched, right? To a certain extent, those physical registers still maintain their value. They have not been touched. So the architectural state is still there. It is still intact and it is still there, right? And the program counter, of course, we can add it into every ROB entry. So we just need to restart from the program counter. So in a certain sense, the architectural state is still intact. We just need to restore the state, in the sense recover the state that existed just before the branch was fetched. We need to go back to that point and start re-executing everything. Now that we know the correct target and the outcome of the branch, at least this branch will not suffer from a misprediction. So what do we precisely need to do? Well, we need to roll back the architectural register state, or recover the architectural register state of the last committed instruction, which is the instruction that was committed just before the branch. The contents in the rest of the physical registers do not matter. In this case, we are only concerned with the contents of the 16 architectural registers. Alright. So we are only concerned with their contents. And so we somehow need a way to kind of recover and rewind our state to the state that existed just before renaming. You can call renaming, fetching, decoding, doesn't matter, but just before processing the branch instruction, in program order, whatever was the state, we need to roll back to that point. So we will discuss 4 approaches for state recovery. The 4 approaches have different pros and cons. They are also arranged in an increasing order of complexity. The first 2 are more commonly used, the next 2 are not that commonly used. But nevertheless, we will discuss 4 approaches. Here is approach 1. The first approach is rather simple. So I will not vouch for its efficiency, but in terms of sheer simplicity, it is clearly the most straightforward. In hardware, many a time we prefer simple designs because it is easy to design and verify many of these protocols, and simplicity by itself has its merit and value. So what we do is that we introduce a new register file. This is an architectural register file, mind you. It's called the RRF, the retirement register file, which if there are 16 architectural registers, it will have 16 entries. And let's assume that we are committing an instruction of the form add and then the value that we compute R5 plus R6 is equal to 10. So what we do is that when this instruction is committed, we also remember the value. So each entry of the ROB is augmented with the value of the destination register. So this does add extra storage, by the way. So a ROB typically has 200 entries. So this does add extra storage in the sense that if it is a 64-bit machine, it adds 64 bits to the size of each ROB entry. So this additional storage overhead is there. But we go to register number R4. In R4 we add the 64 bits, which is the value that was computed. So which means that the RRF contains the retirement state or the state of all the committed instructions. So what state? The register state. So at any point of time it contains the architectural register state of all the committed instructions. Alright. So any point of time an instruction commits, its value is written over here, right? The destination register at commit time. So recovery is very easy because this is sort of a commit time. This is called a checkpoint. A checkpoint is nothing but the record of a state. So anytime we want to recover, well, no problem. If the branch is at the head of the ROB and we find it as mispredicted, not an issue. We flush the pipeline and the entire state of the RRF is written to the physical register file. So what we do is we need to create a new mapping in this case. So the rename table also should be modified. I'm not showing that. So what we can do is that so since we are cleaning up the pipeline, we have the liberty to also clean up all the mappings and start a fresh state. See, if let's say our registers are numbered R0 to R15, architectural registers that is, then we can map R0 to P0 in the rename table, and in the entry for R0 we can write the contents of R0 from here, right? In the entry for R1 we can write the contents of R1 from here. So we essentially need to transfer this entire state, R0 over here, R1 over here, R15, R0 will come to P1, R0 will come to P0, R1 will come to P1, so on and so forth. But at least the first 16 registers here can just be made a copy of the architectural registers, and the mapping can be set in such a way. R0 to P0, R15 to P15, and this is because we are essentially starting afresh. So we have the liberty to change the mapping. We do that and we copy the state of the entire architectural register file to the PRF. So this is undoubtedly a simple method, because what we are doing is we are like doing a fresh start. The entire architectural state is being written to the physical registers, and those physical registers are being mapped to the architectural registers in the rename table. So the rename table I should have shown, I'm not showing that. And then we just start from here, and the program will not get to know that it actually suffered from a misprediction or an exceptional event of any kind. So if you look at this, just appreciate the sheer simplicity of this idea. This is like a brute force idea where it is guaranteed to work, because we just are transferring the state of all committed instructions to the PRF and restarting the program from there, right? There is no hidden trick involved. What is the problem? Well, the problem is that it is inefficient. What are the inefficiencies? The inefficiencies are that each ROB entry is being augmented with the value of the destination register. That is one. The other is that the process of recovery is slow, because physically 16 64-bit values have to be computed and the rename table has to be adjusted, right? So those are the overheads. So let us move to approach 2, which does something more efficient. And if you look at it, you can already see a burger, right? So if you can see a burger, it should ring a bell in your head that there is something that needs to be proved, right? So unless something is proven, you will not appreciate the complexity of this design and the correctness of this design. So as I said, burger means the white and gray matter should start churning in your head, and it should tell you that, look, there is something coming up which requires some amount of thinking. Well, actually it does. So much of the out of order logic and the rename table logic and all the other things that we have been discussing, we pretty much tossed out all of that in the previous design because it was so simple. It was simple and inefficient. It turns out that we can make the design far more efficient if we simply realize a couple of things. First, let's ask a question. Why do we need to write the values into the RRF? What is the need, right? The values are anyway there, correct? So the values are anyway there. Well, why do I say so? So that is important. If you can understand this sentence of mine, that the values are already there, you have probably already guessed what I am getting to. But let's understand the inside. Let us say that time flows to the right, and this is the reorder buffer. This is the mispredicted branch. We have some instructions fetched after it and some fetched before it. So let us say that so the branch does not write to a register. So let us say that when we were dealing with the branch, we found that R1 is mapped to PX. Now when this branch instruction reaches the head of the reorder buffer, will R1 still be mapped to PX? That is question 1. And question 2 is, will PX still have the same value or will it have a different value? Well, so this means that we need to think about several things. The first thing is we need to see when exactly is PX released. So PX is released when some instruction, right? When some instruction writes to R1 and that instruction commits. So at the point of the branch, if R1 is mapped to PX, so it is clear that some instruction fetched after the branch would be writing to R1, which would be PY. So it doesn't matter, but it is definitely not before. So if it is not before, then what it means is that when the mispredicted branch actually reaches the head of the ROB, we are guaranteed to still have PX in an untouched form, because the instruction that maybe modifies R1 would not have committed. So PX would still retain its value, and this can be used, so we don't really have to copy any values, right? So let me show and let me illustrate this slightly better. So let us assume that there is one instruction after the mispredicted branch where R1 gets mapped to Py. So of course after this instruction is renamed, all subsequent instructions will see R1 mapped to Py. But nevertheless Px will still be alive, it will still retain its value. The reason is that this instruction over here, this one, would not have committed, primarily because it would commit only when it reaches the head of the ROB. But before it reaches the head of the ROB, the branch will reach the head of the ROB, and at that point we will realize that it has been mispredicted. Since it has been mispredicted, we will then attempt a recovery, and then we will realize that look, when the branch was being renamed, R1 is mapped to Px. I'll tell you in a second how we will realize that. And then we will also realize that this is the latest value of R1 from the point of view of when the branch was renamed. At that point the latest value was Px. So R1, even though it might have been mapped to other registers like Py, we should restore the mapping and we should again map R1 to Px. Since Px has its value intact, restoring the mapping itself is sufficient. So let us go through the text first and then I will explain this diagram. So what we do is we maintain a copy of the mapping of the destination register in the ROB entry. So in this case, in the ROB entry for the branch, I take the previous sentence back. Let's look at the example. Let's assume that R1 is mapped to R1. There is an instruction add R1, R2, R3 where R1 gets mapped to Py. Then we maintain this R1 to Py mapping in the ROB entry. Alright, so which means that if let's say there is one instruction over here where R1 gets mapped to Px, right? Then we maintain the R1 to Px mapping in the ROB entry of this instruction, and later on when R1 gets mapped to Py, we also maintain that in the ROB entry of that instruction. So whenever an instruction commits, so let's say at this point an instruction commits where R1 is getting mapped to Px, we will update what is called the retirement register alias table, with R1 in the RAT as Px, right? So which basically means that from the point of view of this instruction, R1 and Px contains the latest value of R1, and since this is committing from the commit stream from the point of view of all the committed instructions, the retired instructions, Px contains the latest value. Similarly, if this branch would not have suffered from a misprediction, we would have ultimately committed R1, this instruction where R1 is mapped to Py. At that point of time we would have updated the retirement RAT with R1 and Py. So what does the retirement RAT contain? It essentially contains a mapping of the 16 architectural registers to the corresponding physical registers in the physical register file. So since the architectural register can actually since the mapping of an architectural register to a physical register changes, you will have several physical registers that contain the value of an architectural register at several points of time. So given that fact, what the RRAT basically contains is it contains the contains the commit time checkpoint, or it contains the fact that what was the mapping when this instruction was being renamed. So that would be the latest mapping from the point of view of this instruction. So we keep on updating the RRAT with this mapping. So what is the advantage of doing this? Well, the advantage of doing this is like this, that when we want to recover, right, so let me draw the same diagram again and then I will talk about what is the advantage. So this is the mispredicted branch. There are two instructions over here. First, where R1 is getting mapped to px is the earlier instruction. This is the later instruction. So this instruction is committed. When this instruction was being committed, we go to the entry corresponding to R1 and we write px over there, which means that from the point of view of this instruction and all the instructions fetched before it, px contains the latest value of R1. Or in other words, when this instruction was being renamed, just after it was renamed, px contained the latest value of R1. Next, assume we commit a few more instructions but nobody writes to R1. Then we arrive at the branch. When we arrive at the branch, we will again find that R1's latest value is in px, and this value should be written to the actual register alias table rat. But it is possible that by that time R1 has been mapped to py, which means we have fetched and renamed this instruction. So for R1 actually py is written, right? Let me write py over here. But since this instruction is being flushed from the pipeline, it is being removed from the pipeline and it is not being committed, what we need to do is we need to get rid of py. So let me use my eraser to get rid of it. So we get rid of py over here, and instead what we do is that we write px. So this is equivalent to, tantamount to, restoring the value of R1 to that value which was the latest when this branch was being renamed, right? Which was px, not py. We do the same for the rest of the architectural registers, and this can be done. I will tell you why it is efficient in a second. But after doing that, we will have a set of 16 physical registers that contain the value of the committed state when this branch reaches the head of the ROB, right? It holds the architectural state for all of these instructions that are before the branch. And if we just restore the mapping instead of the values, it is good enough. So what is the, if I were to compare this scheme and the previous one, what is the advantage? Well, first, before discussing the advantage, you need to prove slightly more rigorously that this is actually correct. What is correct? That transferring the mappings is sufficient. You don't have to record the values and transfer the values, right? So we just remember the mappings and transfer them. So transferring the mappings is good enough. So that's the reason instead of storing the value, which is a heavy 64-bit number, we actually store a 7-bit number if we have 128 physical registers. So transferring the mappings is good enough. So this again, I have given you sufficient pointers. Furthermore, more rigorous proof should be done. Once we have convinced ourselves of this fact, let us compare the RRF and the RRAT. In the RRF, we transfer a total of 16 times 64 bits, 16 architectural registers, multiplied with 64 bits per register. In this case, we transfer only 16 times 7 bits, because 7 represents the size of a mapping. So as we can see, in terms of the number of bits transferred, this is roughly 9 times more efficient, which means it is much faster as well as more power efficient, and it also utilizes the built-in support that we have for out-of-order execution, in the sense that if the value is already there, all that we need to do is we need to update and adjust the mappings, right? Just by adjusting the mappings, we can effectively recover to the state that existed when the branch instruction was being renamed. That was the latest state, right? So we can recover to that just by updating the mappings. Now let us look at the third design. So in the third design, what we do is that instead of recording something or doing some bookkeeping whenever an instruction is retiring, we explicitly consider the fact that most of the exceptions will happen when we actually encounter a branch, right? So let us assume that at other points exceptions will not happen. Even if they do, we have some mechanism of ensuring that we pretty much record state only when we encounter a branch, right, or at other periodic points, but not for every instruction. So for every instruction we don't read or write a register at commit time, right? So we don't do reads or writes at commit time, because that is the biggest disadvantage of the previous approaches, that whenever an instruction is committed we need to read something, we need to write something. This is not power efficient. So what we can do is, if we are considering only branches and the only source of flushing and recovery is a branch misprediction, whenever we encounter a branch we should maintain a checkpoint. So what we can do is that whenever we see a branch, we simply take a checkpoint of the rename table, which is essentially a set of 16 7-bit IDs, 112 bits total. So what we can do is we can architect the rename table differently. So in the rename table previously we just had one 7-bit field along with the available entry, of course, so I'm not discussing that. So we just had pretty much one 7-bit field to record the physical register ID. So what we can have is we can have a circular shift register, where instead of 1 we can think of this as a linked list, right? So just think of it as a linked list. So to create a checkpoint, all that we need to do is that we need to record a column of these mappings, which can be seen better on the next slide. So what we do is that we update the rename table such that each entry is a linked list. So what we do is that each of these entries are 7 bits. We create a linked list of such 7-bit entries, and then whenever we want to take a checkpoint, right, this is what we do, that we shift all of these entries one step to the right. So we shift all of them one step to the right, assuming we have enough space, that is, we shift all of them one step to the right. So this essentially becomes an instantaneous snapshot of the rename table. This becomes an instantaneous snapshot of the rename table for a different branch. And finally the last one essentially becomes the architectural state for the branch that is at the head of the rename table, right? So this becomes the architectural state. Why? Well, because this captures the state of the rename table for the last branch, and if this branch becomes the earliest, then this mapping is essentially what we need to restore. And this would be very simple. We just need to move the latest mapping pointer over here. So recovery is very fast. And to create a checkpoint is essentially a snapshot of rename values. All that we need to do is we just need to transfer the values in these registers one step to the right. The same way that we operate a shift register or a linked list, we just take all of these values, transfer them one step to the right, and this is our latest rename table, which we can keep on updating. There's no problem, this we can keep on updating. But whenever we want to freeze it, essentially take a photograph, instantaneous photograph of it, all that we do is we just shift it one step to the right. So once it has been shifted, it cannot be modified again. It's like an immutable photograph which cannot be changed. And it's basically a copy and a shift. So let's say for register R1, P6 is written. So what we do is when we shift it, we maintain P6 here, then we shift, I'm assuming there are other columns, so we just shift them here, shift this one here, shift this one here, and ultimately when this becomes empty, we write P6 over here. So recall that when we are creating the checkpoint, this column and this column will be the same, but gradually, since this column is meant to contain the latest mapping, it will keep on changing as new instructions keep getting renamed. Once if we want to take a checkpoint, we follow the same strategy where we right shift all the previous checkpoints, because each one of them contains a checkpoint. Right? Each column in a sense contains a checkpoint. So all that we need to do is we need to right shift all the checkpoints, create space for this, and transfer the contents of all of these over here to this column. So this is advantageous, no doubt. One advantage is that recovery is quick. So while recovering, we don't really have to do much. In the sense, all that we need to do, if I were to consider a physical implementation, so these are not really linear linked lists, but these are essentially circular linked lists with one pointer to the latest mapping. So all that I can do is I can move the pointer of my latest mapping from here to actually here. So this will give me the, one sec, I'll probably clean the screen and show you. So the pointer of the latest mapping can be moved from here to actually here, which will tell me that look, we have discarded all of these checkpoints, right? All of these checkpoints contain irrelevant data now. This is the only checkpoint that we need to use, and for us this is the latest mapping. So the execution can begin from here. What is the disadvantage? Well, the disadvantage is that each entry of the rename table is now a linked list, right? Essentially it's a circular linked list. We can also call it a, so physically you will implement it using a shift register. That's one disadvantage. And the other is that if, let's say, an arbitrary instruction suffers from a fault, we can only recover to the nearest branch. So that will complicate some of the logic for maintaining precise state. But that of course can be fixed in the sense that if you are recovering to the nearest branch, then the state difference between the current instruction and the branch, that difference has to be recorded. But that's not a major issue. It is something which is solvable. Let us now come to the fourth scheme, which is more complicated. Many of you also might not have the adequate background to understand this scheme. So in this case, we architect the rename table differently. So a traditional rename table actually uses a structure called an SRAM. So a static RAM and a CAM can be picked up from two sources. The first source is chapter 7 of this book, where this concept is explained rather briefly, or you can look it up in chapter 6 of the older book, Computer Organization and Architecture, McGraw-Hill 2015. So in that book, if you go to chapter number 10, then SRAM and CAM arrays are described in great detail. So an SRAM array is like a regular array where we essentially have entries and we have indices. So essentially, if we are talking of entry number 3, it points to this point, the third index. If you start counting from 0, well, no problem, 0, 1, 2 and 3. A CAM array on the other hand is like a hash table. So for a CAM array, we basically have an array of keys and an array of values. So both contain the same number of entries. So what we can do is that we don't search by index, we search by the key, and what we return is the value. In many cases, the value field can be empty. We just search by the key, and the index in which the key matches, that is the value. Right? So in many cases, that is what we want. We want to find out where the key is in a large array. If it's at the 59th entry, the value is 59. That is a legitimate variation of a CAM array. But regardless of which flavor we are using, we need to think of a CAM array pretty much as a hash table where we search not by the index but by a multi-bit field. The multi-bit field in this case is being referred to as the key. Alright, so I mean, the basic abstraction is that an SRAM array is like a regular array, but a CAM array is like a hash table. So it is possible to implement the the register alias table, using CAM arrays. So what we can do is we can have 128 entries. Each of these entries will contain two things, right? So if I were to see one entry, so each entry, right, I'm just blowing this thing up. So each entry will contain two things. It will contain the architectural register ID that the given physical register is mapping to. So why 128? Because we have 128 physical registers, and let's say I want to find out which physical register is R5 currently mapped to. So in the previous approach I will just index the fifth entry, but in this case I'll not do that. In this case what I will search for is I'll search for 5, which is 0101 in binary, and also the mapping should be valid, in the sense that what we have discussed in the past is that there might be multiple physical registers that map to R5 in the pipeline at the same time. One of them will be the most recent, let us call it valid, and the rest invalid. So we want the valid bit to be 1, which means it's the most recent mapping, alright, and also that it is mapping to R5. So what we need to search for, what the key would be in this case is 0101 corresponding to R5, and the fact that it's a valid mapping, the most recent mapping. I search for this within the CAM array. I am guaranteed to find only one entry that matches, and the index of that can give me the physical register ID. So let us say that this maps to the 28th entry, and here we find out that it contains 0101. Then I say that R5 is mapped to P28. So if you think about it, this in itself is a valid way. I won't say it's a common way, but it is undoubtedly an extremely plausible way of implementing a register alias table, where instead of implementing it as an array, we implement it as an hash table. So in this case we'll have a CAM array, and the CAM array will pretty much have two columns, the architectural register ID and the valid bit. The valid bit indicates that it is the most recent mapping. So when we search, we concatenate the architectural register ID with 1, which indicates we need the most recent mapping for a given architectural register. So I'll just clean up the ink on this slide such that at least you can see the animation. So it is a 4-bit architectural register ID and a valid bit is what you get for a 7-bit physical register ID. So 7-bit physical register ID need not be a part of the entry. The index in which this information is found can represent the physical register ID. So now let us see how a CAM based RAT actually works. So the key points over here are that at any point of time 16 bits are set to 1, because only 16 architectural registers are what we have. So this is the set of 16 entries in the RAT table, and we can save a snapshot of these. So this is an important point in a graphical form. So there is an important thing that needs to be understood. So a lot of people find it very hard to understand this scheme, and the entire crux of the problem stems from the last statement that I made. So you need to understand that there are 128 entries in this structure. This structure is a hash table, which we are calling a content addressable memory or a CAM. Each entry of this CAM contains an architectural register ID. Let's say if we are talking about R5, then it is 0101 and a valid bit. So the valid bit is an important concept, and in fact it is the most important concept when you are discussing this. So it is possible that in our pipeline we might have 4 instructions fetched at different points of time that pretty much write to register R5. So the earliest one might be write R5. You would have mapped it to PX. The next one might have been mapped to PY, and the next one might have been mapped to PZ. So all 3 of these mappings will exist in our pipeline, but clearly the R5 to PZ mapping will be the most recent. So the valid bit for the PX and PY entries will be 0. The valid bit for this will be 1. Alright? So whenever any subsequent instruction comes and it tries to see which physical register is mapped to R5, it will essentially search for this value in the CAM, which is 0101 and 1 because of validity, and that would point us to this entry, which is the entry for PZ. Alright? So this is the crux. So regardless of the fact that many instructions might be mapped to R5, of course capturing different points of the execution, only one will be valid. The same holds true for other registers. So it can be proven that this column, the column of valid bits, will have these properties, right? So I have provided an informal proof, but a formal proof is something that you can work out on your own. It's easy, it's not that hard. So the first is that only 16 out of 128 valid bits are 1. That should be obvious because we'll have 1 valid bit per each architectural register, and there are 16 such architectural registers. The other would be that essentially it is 1 valid bit per architectural register, which is just a rehash of the previous statement. Alright, the rest remains the same. So here is the key insight. Alright, so let me draw a small bulb. I'm not a good drawer and I'm not a good artist, that too with a tablet. Still I'm trying my best. Alright, I seem to have done an okay job. So what I'm trying to say over here is the key insight is that since registers tend to maintain their value, right, until another register that writes to the same architectural register gets committed. So it's the same insight as the previous approach 3. What I am saying, or rather I am claiming, is that checkpointing the column of valid bits is sufficient. Checkpointing essentially means storing. Right, so this is sufficient. All that I need to do is that this column that essentially contains these 1-bit numbers, this column of valid bits, if I just checkpoint it, if I just store it, then I can easily restore it. So which basically means that for a branch, instead of having to deal with 7-bit numbers, so instead of having to deal with 16 7-bit numbers, where of course moving them in principle will take 7 clock cycles, I can have one thin and narrow column of 128 1-bit numbers, and as far as I am concerned, these 1-bit numbers, a sequence of 128 of them, they represent a checkpoint, and what I can do is that I can just roll back and restore a checkpoint rather easily. So if you think about it, if we look at it in the context of this example, I can do this for R5 and you will see that it will be correct. So let us consider the execution at this point. At this point, clearly PZ is the latest mapping, and what we see is that the rest of the mappings to PY and PX are outdated and old. Now let us assume that a branch misprediction happens over here. So one branch misprediction over here happens. So which means that at this point we don't do anything, we wait for the branch to become the head of the ROB. When it becomes the head of the ROB, then the mapping of R5 to PX is a part of the committed state, correct? And R5 to PY is an interim value and R5 to PZ is the latest. So let me name them. So this is a part of the committed state, right? So because this has been written, this instruction has been committed. This instruction is interim, which means that a write has been done but the instruction is not committed. Consequently, we have not released PX because this instruction is not committed, R5 to PY, and this is the latest. So what do we do? What we need to do over here is the first thing that we need to do is essentially change the color, and I'm changing the color of my ink. So we pretty much need to cancel this part of the execution because this is potentially on the wrong path, and we need to roll back our state to this point. If we need to roll back our state to this point, we pretty much need to restore the values of all the registers that existed at this point. So we have already seen in approach 2 that restoring the values is a slow operation. What we should instead do is that we should restore the mappings. So for restoring the mappings, what we need to do is that we will have a bit vector that would have stored the mapping for the current, for the branch corresponding to this. So there will be a mapping corresponding to this branch, right? So the mapping that would correspond to this branch would have a 1 over here for PX, because for it PX is the latest mapping of R5, and for the other two, well, we don't really care what it contains because those are not relevant. So let me put a question mark because we don't care. So when we restore the mapping for this branch and we start our execution from here, we will pretty much start, sorry, this doesn't look like a question mark, so let me put a cross because the mapping doesn't really matter. So what we would do is we will restore this entry as the valid bit for register R5, alright, and then this is effectively the same as changing the mapping in the previous approach, but in the previous approach we were actually copying the mapping a 7-bit physical register ID. In this case, all that we do is in the PXth entry of this CAM based RAT, instead of 0 we just convert it to 1, and naturally over here, since this entry is replacing this, if 5 is written over here for PZ, then of course this gets converted to 0, But if this is mapping to some other architectural register, then we don't care. So, but the most important point is that for Px the mapping becomes 1, which means that Px becomes a Px now contains the most recent value, which actually it should, right? Because the rest of the instruction state anyway we are getting rid of. So this actually it should. So this basically tells us that the process of our checkpoint creation is much faster, because in this case we are dealing with single bits instead of larger 7-bit quantities. So dealing with them is much faster, right? But of course the CAM itself is slower than a basic SRAM. In a sense, a hash table is always slower than an array. So that issue notwithstanding, since we are dealing with single bits, we can look at this as a faster alternative subject to other constraints. So now let's go back to the slideshow. So essentially for every branch we take a snapshot of the valid bits. The best way to achieve this is to have a shift register with each row, similar to what we had in the previous design, and we use the same idea as the SRAM based RAT. So what do we do? Well, in this case what we do is we have a list of mappings, where this is of course the current mapping. Then we have a field of architectural registers. So this will remain the same. Only thing that will get checkpointed are these 1-bit columns. The checkpointing logic also happens in the same way. So how does it happen? Well, the way it happens is whenever we want to take a checkpoint, we just right shift everything. So these are internally organized as circular queues, which is a recurring pattern that we are seeing in hardware. So pretty much this moves over here, this here, this here, this here, then this here. And whenever we want to recover, we pretty much take the rightmost entry, right, or rather the head of the queue, the earliest entry of the queue, the head of the queue, and then we recover our state to that point. So this, mind you, is a much faster option, because each of these entries is 1 bit instead of 7 bits. Hope it's clear. So now we are in a position to look at the pros and cons of all 4 schemes. So the RRF is clearly simple to implement. Transferring the checkpoint is easy. It does involve extra register writes every cycle. We need to save fat values, and that too in the ROB. So space is a concern, power efficiency is a concern. So I would say RRF is simple. It's not something that you would always want to use if you want to create a high performance processor. What you should instead use is an RRAT, where you require less space, but the point is that transferring the checkpoint etc. is much faster, because you are dealing with mappings and not with values. It still has activity every cycle. If you are not happy with activity every cycle, you just want to have it on a branch, well then use an SRAM based RAT checkpointing scheme. But well, what do you do if a normal instruction has an exception? Well, you need to recover to the nearest branch. What about the instructions between the branch and that instruction? Well, then you need a smaller state buffer for that. What if a code that doesn't have branches for a long time? So for all of these, I would there are simple solutions that require some amount of bookkeeping or some amount of forced checkpointing. So this is left as an exercise for the viewer to figure out a solution of creating a practical form of this. A CAM based approach is, needless to say, much more efficient than an SRAM based approach, because we are only shifting 1 bit. But the overhead is that you are using a CAM which per se by itself is a slower structure than an SRAM. Alright, so we have successfully ended our journey of this very long chapter on the rather intricate aspects of an out of order pipeline. But at least you'll be happy to know that the out of order pipeline is complete. So some of the key points: renaming is done using the RAT table. between architectural and physical registers. We do need a free list and dependence check logic. Wake up, select and broadcast are the core mechanisms that comprise instruction scheduling. The LSQ manages the dependencies between loads and stores, forwards data between in-flight loads and stores. And the reorder buffer is a very important buffer that keeps track of in-flight instructions. And when they complete, they are said to be committed. And of course, we need a method of state recovery to move back in time to restore the state that existed when a given branch was being renamed. Alright. So in the next chapter, chapter 5, we will study more complex mechanisms in out-of-order processors. And we'll also look at how the compiler helps make processors more efficient. Right. So what we can do at the compiler level to make the process of dealing with instructions, to make processors essentially way more efficient. Alright, the end. Thank you very much. See you in chapter 5.